All right, continuing on, we're going to be using metric prefixes quite a bit in this course. You will need to know how to use metric prefixes in expressing our quantities for the measurements of length, mass, and time, as well as additional units that we'll use that combine those three quantities in various ways. You've probably seen the metric prefixes. There are a lot of metric prefixes, but these are the ones that you're responsible for. That's nano, which is 10 to the minus ninth. The abbreviation is a lowercase n. That means, like for example, that 1 nanometer, for example, is 10 to the minus 9 meters. And that's what this number means. That a nanometer just means that I'm saying 10 to the minus 9 meters. All right? Micro, milli, centi, and then we go from smaller measurements to larger measurements. So kilo. So for example, kilo is 10 to the third. So for example, 1 kilogram is equal to 10 to the third grams, or 1,000 grams. Mega and then giga. Or if you want to be really cool, my advisor in graduate school said that giga should not be pronounced giga because it's like gigantic, right? Gigantic. You don't say gigantic, right? It should be gigahertz or gigameters, gigahertz, whatever. So anyway, if you want to be cool, you should not pronounce giga giga. You should pronounce it giga. Well, I'm not that cool, so I'll just say giga. All right, so those are your metric prefixes. More about that later because we'll need to convert between different metric prefixes. So for example, going from nanometers to meters, grams to kilograms, megameters to millimeters, that sort of thing. All right. Dimensional analysis is really just a way of checking your units and checking your equations. And it's kind of a useful tool that hopefully you'll use throughout the semester because it helps you to just verify that you're doing something correctly if you have the units correct. Though in this chapter we'll have explicit assessment on it, that is that you'll have explicit questions both in the online quizzes and in the exams. We'll use dimensional analysis to solve or check a problem, and we just treat our units algebraically. Now first, before I show you some examples, I just want to give you some common dimensions and units. So for example, area, which is a length squared, is measured in square meters. Volume, which is length cubed, I measure, of course, in cubic meters. Velocity is length over time. Or maybe more correctly, we would say speed is length over time. And so that's going to be meters per second. Acceleration is length over time squared. And that's going to be, of course, units of meters per second squared. Okay, so in a question on the test, you'll have something like this. I'll give you some equations. For example, here, I have 3 different equations, and you'll need to tell me, are these equations dimensionally correct or not? And the way that you approach these is you just take the units for each variable and put them into where the equation. So for example, I have x, which is a measurement of length, and so I'm going to put that in as meters. I have v, which is a measurement of velocity or speed, and so I'm going to have meters over seconds. And I have t, which is a measurement of time, so I'm going to put in seconds. All right. And then I ask myself, are the units on this side the same as the units on this side? And I can see here that the seconds cancel, and I'm left with meters equals to meters. So they have the same units. That was pretty easy. They get a little more complicated, like for example here in part B. First of all, just let me say a couple of things. One, this subscript right here, a little 0, that means at time equal 0. I'll say this is, I'll say, for example, that this is x naught. Right? We might also call it the initial x or the initial position. It's a pretty common way to describe the initial conditions for a particular variable. So it doesn't mean anything. It's still measured in meters. So here I have meters for x. X naught is also measured in meters. And that just tells me what is the position or what is the distance at time t equals 0. And that'll become important later in the next chapter. But for now, we just need to know that the units for this are just meters, that it doesn't really affect what we're doing. Similarly here, with v naught, or the initial speed, doesn't change the units. I'm still meters per second. My time is in seconds. Now, the second point that I want to make is that anytime we have a constant like this 1/2, a constant has no units. So that 1/2 has no units. I don't need to do anything with it. In fact, when I write out the units of this equation, I'm just going to forget about this completely because it doesn't impact the dimensional analysis of the equation. A was acceleration. That's meters per second squared. And time squared is seconds squared. And I want to ask myself, are the units on this side the same as the units on this side? And what we're going to need to do is check the units for each of these individual parts. And they all have to have the same units as over here. So I'll write that here. On the left-hand side, we had meters. Here, I have meters. Notice the seconds cancel left right there, so I'm left with meters. Notice the seconds squared cancel there, so I'm left also with meters. So I have meters here, and I also have meters here, here, and here. So that tells me that that equation is dimensionally correct. So is that equation dimensionally correct? Yes. Similarly up here. Is it dimensionally correct? Yes. Now let's look at this next one. So I have V, which is in meters per second. I have A, which is in meters per second squared. Folks, here, I'm going to write this a little bit differently. I think it'll help you a little bit. I'm going to write it as A times 1 over T. And that's the same expression. So I have A, which is meters per second squared. And then I have 1 over T, which is 1 over seconds. Plus, remember that 0.5, the units on that, there are no units, so I'm just going to leave it off. X is a measurement of length, so that's m, and then t is seconds. So you can probably see right now, I'm going to do a little simplification, but you can probably see that the units here don't match up. So I have meters per second here. I have meters per second cubed, and then I could just stop right there and say, no, this is not dimensionally correct, plus meters times seconds. So in none of these cases do they match up. Now, let's say I could have an equation that looked like this. Let's say that I had meters seconds equals meters per second plus meter seconds. Now, would this equation be dimensionally correct? Well, yeah, I have a match here and here, but there is no match here. So the answer for this one would be no. It is not dimensionally correct. This is your quick test. Let's see, I had a little mistake here. Let me fix that. That's a meter per second. Is this equation dimensionally correct? Okay, you want to take it, put in the units for the variable, and determine do the dimensions, are they consistent? That'll be on your online test. We'll stop there and pick up with uncertainty next time.